Look at the sugar bowl sitting in your kitchen. The contents are pure white, dry, geometric crystals. But those neat little shapes come from 10-foot-tall, thick, rough, woody grass. To grasp how that transformation happens, we have to look at the sheer scale of the raw crop. Up to 70% of that towering stalk is just water. The valuable sucrose you want is trapped deep inside what is essentially a massive biological water bottle. This cross-section maps the problem. Accounting for the huge blocks of water and fibrous matter leaves only a tiny sliver of sugar. And there's a biological ticking clock. Once severed, that sucrose rapidly degrades. Extracting it means putting manual laborers out in the fields, hacking through tall, dense, often charred cane under brutal conditions. Then, thousands of tons of heavy, rotting plant matter have to be loaded onto trucks and rushed to the factory gate before the sugar content collapses entirely. The entire industrial process that follows is a high-speed race to brutally strip away 99% of the plant's volume to rescue the 1% we actually want. The moment those stalks arrive, the factory begins the process of subtraction. First, high-pressure washes rip away the field dirt, mud, and dry leaves. Next comes the violence. Clean stalks are fed into massive iron rollers, physically crushing the grass to force out liquid. But a single pass leaves too much behind. The cane is squeezed again and again under immense pressure, wringing out every possible drop of juice. What survives this crushing process is called bagasse, a dry, shredded, woody fiber. Since the factory processes millions of stalks, this waste fiber piles up into literal mountains. But it doesn't go to a landfill. The factory feeds this bagasse directly into its own giant furnaces, generating the heat and electricity required to run the machinery. The extraction process harvests the sugar, while simultaneously extracting the exact fuel needed to power its own operation. Meanwhile, the liquid we crushed out of the cane isn't ready for your tea. It is a muddy, cloudy green juice full of microscopic soil and organic impurities. To fix this, engineers use a process called clarification. By injecting specific chemicals and applying heat, the dirt and floating particles bind together, grow heavy, and drop out of the liquid entirely. This liquid volume chart highlights the next hurdle. The clear juice is still mostly water, meaning immense amounts of liquid must be boiled off. Inside giant evaporators, the liquid boils continuously. As water vaporizes, the juice concentrates down into a dark, incredibly thick syrup. Through targeted chemistry and raw heat, the factory eliminates the biological water weight entirely, leaving behind only the dense, sweet essence of the crop. Now, engineers have to force that thick liquid to become a solid. The syrup is pumped into vacuum pans, where the boiling temperature and artificial pressure are tightly manipulated. Under these precise conditions, a microscopic state change triggers. Perfect, flawless geometric crystals spontaneously form and begin stacking together right out of the chaotic syrup. At this stage, the factory has produced massecuite, a heavy, slushy mixture where those newly formed solid crystals are trapped inside a thick, sticky liquid. To tear them apart, the mixture is pumped into highly specialized industrial machines called centrifuges. The centrifuge spins at dizzying speeds, generating intense force that throws the heavy liquid outward through a perforated screen. Solid crystals remain trapped. That dark liquid, molasses, is piped away for other products, leaving behind a thick wall of pure white sugar. Tearing a dense biological liquid apart into a dry solid requires pushing physical forces to their absolute limits. Those raw crystals still carry trace amounts of moisture. They are blasted with intense hot air to dry them out, then shaken over vibrating metal screens to sort them strictly by size, fine, medium, or large. Before anything leaves the building, samples undergo rapid-fire laboratory tests. Chemists check the exact moisture content, test for chemical purity, and ensure the color is perfectly consistent across millions of individual granules. Once approved, the crystals flow into automated packaging lines, filling endless rows of sacks that stack up into vast warehouse-sized oceans of pure sugar. A spoonful of sugar is the final zero-waste triumph of agriculture, chemistry, thermodynamics, and industrial engineering.